In the previous lecture, we discussed about the computation of principal component analysis and how we can find out the lower dimensional representations of data points which are represented in a particular space. Now, let us consider what are different kinds of applications those are possible using PCA. Now, I will consider three major applications here. So, one of them is say data compression. As you have already seen directly that actually you do not require that many dimensions to represent data, that itself gives an efficiency of data representation. It requires less storage for representing data. So, it provides an optimum set of orthonormal basis vectors for a set of data points, because we have seen in the case of image transforms that orthonormal basis vectors, they are very convenient to transform any data point into another space, and if your basis vectors are properly chosen, then you can reduce the redundancy of that representations. So, in PCA you have that advantage. Actually, it is the optimum set of orthonormal basis vectors which will give you that kind of transformation. But it is data dependent, that is one issue here. So, for every set of data points you need to perform this analysis and then compute a new set of orthonormal basis vectors, which is not very convenient from the point of view of data compression, because with the compressed data then you have to also convey this information of orthonormal basis vectors, which is an overhead for this. However, and these basis vectors, they are called Karhunen-Loeb basis, or the transform is called Karhunen-Loeb transforms, which is an optimal representation of data, as I mentioned. In fact, many standard basis vectors, they can be shown as eigenvectors of certain statistical representation of signals or images. For example, type 2 DCT basis vectors are shown as it is approximately the eigenvectors of 2D matrix with jkth entries as r to the power j minus k, as it is shown here. So, this r, it represents the correlation between adjacent samples. So, j and k. So, if j and k is deviates too much from that location, then it is not, adjacency is less, and then the correlation should be less. So, because r is a value which is less than 1. So, as the j minus k, this magnitude increases, it will be reducing, this value will be decreasing. So, you have less correlations, but for high correlations, for adjacent samples, it is expected they should be very highly correlated. Now, with this kind of data, it has been shown that the basis vectors are that means eigenvectors are almost similar to the type 2 DCT basis vectors, and that is why type 2 DCT is so efficient for representing a large class of signals and images. So, as I mentioned, covariance matrix for a very useful class of signals, where R is the measure of correlation between adjacent samples and it is a value near to 1. So, it is trying to represent the natural images and natural signals with this kind of statistics. It is trying to model that part. The other advantage of PCA or other which is used also different applications, that it decorrelates the components. We have already seen in the example that covariance matrix, they show that there is high correlations between different components for the original data, but after performing PCA, actually those correlations are largely reduced. So, it will be almost 0 in that case, ideally it would be 0. So, that is how it decorrelates the components. So, one of the applications of this kind of using this property is that you can find out a new color space. You know that when color images, they are represented in RGB color space, they are highly correlated. So, there is a work, I have given this reference here. It is the work done by Ota, Kanade and Sakai. So, what they did, that they took a large number of color images and they performed PCA using the different blocks of those color images, and then they found out eigenvalues and eigenvectors, and those eigenvectors, that gives you the new transformation space. So, in fact, they found that if I transform the color component using those eigenvectors in this way, that r plus g plus b by 3, r minus b is the second component, and 2g minus r minus b divided by whole thing divided by 2, that is the third component. Now, these are the principal components from their principal component analysis, and as you can see, this is nothing but you are performing a color transformations where the first one is indicating the intensity value and the other two, they are the chromatic components. So, this has been obtained through this PCA itself. The major applications of PCA, it is there when you have more number of components in images. So, color images, they have only 3 components, but if I consider remote sensing images, these components could be very large. There are different kinds of remote sensing images depending upon the bands they are using, depending upon the electromagnetic wavelength bands they are using. So, multispectral, hyperspectral, ultraspectral remote sensing images, and there could be many bands. So, like multispectral, it could be tens of bands, hyperspectral, it could be hundreds of bands, ultraspectral, it could be thousands of bands. You have so many different bands, so many numbers of bands, and how to get an efficient data representation using those bands. So, what we can do, so which means that at every pixel it has dimension, data dimension is, say, if it is band number is n, data dimension is n. So, there this kind of dimension reduction becomes very useful. We can find out only those components after reduction, we can reduce those components which are decorrelated and use those components to make the information analysis, to analyze, process the information, or to correlate with different ground truth or different ground level information. So, PCA is required to highlight decorrelated information. This is one example where I am showing that PCA components of a hyperspectral image, and you can see that it starts from this is the PCA which corresponds to the maximum variance, maximum eigenvalue. You have lot of information there, lot of details there, and this is the minimum eigenvalue. In this case, it is actually 20th eigenvalue. Now, if the number of band is, in this case it is not specified, I suppose the number of band is if it is 20 in this case. So, this is the minimum one. In fact, there is no such information, almost no details are visible here. So, that is the advantage of PCA. You can prioritize, or you can give preferences to those bands which are having more informations, and say this is a PCA 1, this is band PCA 2 band, second band, third band. As you progressively go over the PCA components from say top to bottom and left to right by making this kind of scan, you will find finally the details are slowly dying and it gets almost like a smooth region. And so, you can use these components to find out, to analyze the information where it is represented. It is representing those information better here. So, this is what after component 20 not much details are available, and it removes that data redundancy in this representation. The third application of PCA could be factor analysis, and it highlights these decorrelated factors. So, you can find out the factors related to that. Even the color component what I have shown, it is trying to find out those factors, the intensity factors, chroma factors, and this factor analysis, this is very much useful for classification. For example, you consider eigenfaces for representing human faces. So, what we are doing here, we consider a large set of images of human faces cropped to the same size and follow certain rules, like it is not only just simple cropping, you are trying to maintain the different parts of the human face at the similar from the at similar distances from the top, and then you perform PCA, and any arbitrary face you can express as a linear combination of those eigenfaces. That means, if you perform PCA, you get eigenvectors, those are called eigenfaces here. So, coefficients of linear combination, it represent an arbitrary face. So, this is one example that it is showing 4 eigenfaces. So, if I consider any arbitrary face, at least I can represent by a 4-dimensional vector using this PCA, using these factors, and then subsequently we can use it for classification. So, this is the another applications that we use those factor analysis, use those representation for any classification or high level processing, like you can this is a pipeline. So, you can perform factor analysis and then those representation can be used for classification. So, I will be now discussing another another type of dimension reduction. In fact, the objective here is more for the purpose of classification. In the previous slide itself, I have shown how PCAs could be used for factor analysis and those factors could be used for classification, but it is not necessary that those representation of those factors are efficient for classifications, particularly if you are considering linear discriminant functions. So, we will be considering those kind of dimensional reductions where this linear discrimination becomes simple for, in fact, this is a simple discrimination. It's you are reducing it to just 1-dimensional component. So, the objective of this linear discriminants, and which is known as Fisher linear discriminant by the inventor Ronald Fisher, is a very famous statistician, and it captures the direction of maximum variance of a data set. So, for level data set, it does not capture the direction of maximum separation between the groups of data points of different levels. So, here the point is that PCA, it captures the direction of maximum variance for a data set, not the Fisher's linear discriminant. But if I consider the data set is leveled, then it may not capture the maximum separation. So, I will be showing you I will be explaining it with respect to this diagram. Consider there are 2 groups of data points. These are the level data points. One is shown by the triangles, and other groups are shown by ellipses by different colors. Now, the direction of maximum variance is the dotted line. That could be the direction. Along that directions, all the projections of these data points, they will have maximum variance. But if I take the projections, as you can see here, that within these intervals, the projected data points, they are intermingled. So, they are not well separated. So, they cannot be segregated using simple interval rules. They cannot be discriminated by that rules. But whereas, if I consider another direction, say this is the new direction, another directions, and if I take the projections, now you can see that all the projected points for this group, they are lying within this interval, and all the projected points for this group, they are lying within this interval along this direction of projection, along that particular direction. So, they are well separated, and so this shows that the principal component, direction of the principal component is not really providing you the good separations between data points. So, as we mentioned, it is well separated, but not along the direction of principal component. So, let me now explain then that what is the computational problem that involves in this particular analysis, Fisher's linear discriminant analysis. So, consider a set of data points as we have considered in the previous cases also. and then out of those there are n1 data points which are in class W1, and there are n2 data points which are in class W2. So, naturally we consider that n1 plus n2 should be equal to n, capital N, which is the total number of data points. And now you consider a line with direction u, because our objective is to get a direction where this separation could be maximum. So, we should consider projection of data xi on u. So, the projection can be, operation can be expressed as a dot product of two vector xi and u, or in the matrix representation it is ai xi transpose into u, matrix multiplication of xi transpose and u, and that would give you the projection of data point yi. It is nothing but an one dimensional subspace which represents this data. So, all the points are on that, lying on that line. Now, we are trying to measure what is, how the projected data is separated, because with that measure then we can formulate a problem for maximizing that measure to get a well separated data. So, in this case let us consider mean of data points in class W1 is M1 and mean of data points in class W2 is M2, and projection of these means along this direction u can be computed as projection of mean vector along u, that M1 transpose u and M2 transpose u. So, figuratively we can show here that my1 and my2, and one of the measure of separation could be the separation of these two means, that means how far they are. We want this measure should be large, this value should be large for well separated two groups. So, if you consider the difference, absolute difference between these two values, that would give you a separation measure. But the problem here is that it is not capturing the variance of data. So, some data could be very well spreaded, very largely spreaded in an area, and some could be very closely grouped, closely spaced and after projection. So, our ideally what we would like to have, ideally you should have the data points, they should be closely spaced around mean and they should be largely separated. Then only those kind of measures, I mean those are the desirable situations, desirable cases for this projection, but that is not captured by simply by the value d. So, what we do in that case, we normalized this d by a factor proportional to class variance. So, in fact, we call it this factor as scatter. So, scatter of data belonging to class C is defined in this way. It is in the projected space. So, it is nothing but, as you can see, it is the sum of mean, square of mean deviations from the mean, from the mean of the data points, and it is a proportional factor with variance, because it is nothing but class variance, product of class variance and number of samples. And as I mentioned, MC here represents the mean of class C, and small a square is a scatter. So, the measure of separation, a good measure of separations could be that d square by S1 square plus S2 square. In the denominator, we are summing up the scatters of two projected groups. So, when you add them, that acts as a denominator in the denominator, and the numerator is d square. So, it is normalized by the sum of scatters of these two groups. So, scatter of class W1 and this is scatter of class W2, and our objective is to maximize this value Ju with respect to a to get a direction, and so scatter of projected samples should be small. Let us define also scatter matrix of the original data. So, scatter matrix of sample of class C in the original space, that is also defined in the same way. So, it is, as you can see, it is a multidimensional space. So, earlier we have only one dimensional space, subspace for projections. So, we have used standard definitions of variances kind of definitions, that means square error, square deviations, but now we have to use the corresponding outer product of this matrix to denote a scatter matrix. So, this is represented as you can see, x minus m c into x minus m c transpose. This is the outer product of the matrix x minus m c, and sum of them will give you the scatter matrix. So, within the class scatter matrix, that is defined as scatter matrix for S1 and S2. So, sum of S1 and S2, that is within the class scatter matrix. So, each one for S1 you have to consider once again that definition. That means, suppose for S1 we had M1 as the mean. So, the vector x minus M1 into x minus M1 transpose and sum of, if I consider there are ith samples. So, this is a ith component, and if there are n1 samples in S1, so you have xi minus M1 into xi minus M1 transpose, sum of them. That is what is S1. Similarly, you can compute S2 and you add them, that would give you the within the class scatter matrix. Whereas, you note that your scatter matrix for the projected samples are given in small s1 square with this symbol. So, y minus my1 whole square. So, we can show how it is related with this within the class scatter matrix. So, this can be written as in this form. So, you can see that this is what is the projected sample of x along the direction u. So, we can write u transpose x. Similarly, this is the definition of this is the projected mean of the samples along y along the direction u. So, it is u transpose M1. So, this itself can be written as u transpose x minus u transpose M1 into u transpose x minus u transpose M1 transpose. So, we can write in this way, we can simplify this algebraic form, and you can write in this form. You can note here actually, since it is one dimension, so whether I put the transpose here or here does not matter. So, we have taken the convenient form for the sake of derivations, for the sake of the final derivations. So, we can see that from here you can take out u transpose u outside, and this will give you the scatter of the original sample for class W1. And this is the reason why transpose here, instead of taking u transpose x minus, this could be as transpose, and we could have taken this also. On the other hand, we may, and this is also correct. So, but the advantage of this notation is that then we can bring the scatter matrix nicely within this u transpose and u in this form. We can get it in this form. And so, from here we can see that small s1 square is related with the scatter matrix of that class by this expression. So, S1 square is nothing but u transpose S1 u. Similarly, S2 square would be u transpose S2 u, and if I add them, finally, the both S1 square plus S2 square can be written as u transpose SW u, where SW is the within the class scatter matrix as we have defined. Between the class scatter matrix, that is another definition. Now, this is the scatter matrix formed by the means of those classes. So, this is how the definition is there. So, SB is M1 minus M2 into M1 minus M2 transpose. It is the difference between two mean vectors. So, difference vector of means, that is defining the scatter matrix. And here also we can show that the separation is related with this. So, the d square, which is nothing but the square deviation of two projected means, that could be written in this form. Once again, conveniently we have used the outer product form to outer product matrix representation for showing the square of an one dimensional term, and this could be represented as it is shown here u transpose m1 minus m2 into m1 minus m2 transpose u. Now, this part is nothing but this is what is SB, and so you can write it in this way, and that is related with d square. So, it is the same as d square. So, finally, we can rewrite this optimization function as it is to maximize this factor j u, which is d square by S1 square plus S2 square. This could be rewritten as u transpose SB u divided by u transpose SW u. So, this is the problem of optimization, that you have to maximize it. Once again, u should be unit vector, that is a constraint. So, u should be such that it can be shown that SW inverse SB u equal to lambda u, provided SW is invertible. So, I am not giving you the derivations, I am providing you the final solutions, that u is the eigenvector of this particular matrix. It is like an eigenvector solution SW inverse SB, and if you compute the eigenvector there, and since now you want maximization, which means you have to consider the maximum eigenvalue, vector corresponds to the maximum eigenvalue. So, and one of the thing is that interestingly, that SBU it has the eigenvector along already m1 minus m2. This can be shown easily if I consider this particular expansion of SB. So, this is nothing but SB. So, this part, as you can see, that this is the dot product of the difference vector with respect to u, and which would be some scalar value. So, this is some scalar value k. So, finally, this expression is nothing but it is a vector. This is some scalar term. This is nothing but a vector m1 minus m2. So, the eigenvector of SB is also m1 minus m2. So, in that case, the solution of u can be considered as SW inverse into m1 minus m2. That is what is your solution, and in this way you can get the direction where you can get the maximum separation of projected samples. This is how the Fisher's linear discriminant works. So, let me explain it with respect to an example. Consider a set of data points, and now we are considering labeled set of data points. So, we have given you two such sets x1 and x2, and we perform linear discriminant. So, we have to perform linear discriminant analysis or to get the optimum direction, or FLD actually, Fisher's linear discriminant analysis, to get the optimum direction, and we should check also the separability in the line of projections. As an alternative also, we will perform PCA on the whole data set, because PCA does not consider class information. It considers the whole data set and get the dominant principal direction and check the separability of the projected points on it. So, for linear discriminant analysis, or performing here Fisher linear discriminant, we consider this representation of data into two matrices, x1 one group of data, all column vectors are data points, x2 other column vectors are here also column vectors are data points for group 2. So, mean of x1 is given this, that is what is m1, and mean 2 is given this, that is what is m2 in our notations we have discussed earlier, and this is what is your scatter matrix for the x1. So, S1 is the scatter matrix for S1. Similarly, you compute scatter matrix for x2, S2, and within class scatter matrix can be represented. Now, this is the definition of S1, which we have already we have discussed. So, within class scatter matrix is S1 plus S2, which is given this. And now, you know the solution, you have to take the SW inverse and then multiply that with m1 minus m2, that would give you the direction. So, this is what is your u, SW inverse into mean 1 minus mean 2, and it could be found that u value is given this. It could be unit vector also, it could be any vector, because it is just projection. So, magnitude of the vector does not. So, the separability, if you would like to study, you take y1 as the x1 transpose u. So, you are taking the projections of all data points in x1 with respect to u. So, we can perform all these operations simultaneously using this matrix multiplications. Similarly, you consider projections of all data points of x2 with respect to u. So, you will get them as column vectors. There are 3 data points there. So, these are the projections for y1, these are the projections for y2, and you can see that their intervals are well separated, because the range of y1 is 19.31 to 22.2, whereas range of y2 is 5.43 to 9.55, and they are well separated. Whereas if we perform principal component analysis on the whole data set, which is represented here by the matrix X, all column vectors are data points, and you have considered union of data points of x1 and x2. So, for principal component analysis, as we did earlier, first we compute the mean vector S bar, then we compute the covariance matrix, you note the variance of data. So, sum of diagonal elements, that would give you the total variance of the data, and if I compute the eigenvalues and eigenvectors in order of their values, I am showing here. So, the maximum eigenvalue is 72.96, and eigenvectors, corresponding eigenvectors are this E1, E2, E3, and we are interested on finding out the directions of maximum eigenvalue or maximum variance. So, this is your principal component, direction of the principal component is given by E1. So, if I take that direction and check the separability of projected samples, so we perform the same projections on that direction, and these are the values we will get. We will see that at least there is one sample, this is a toy example. So, I mean it approximately it is good well separated, but there is at least, compared to the previous one sample is there 13.98, which lies in the interval or very close to the interval of the data points of Z2. So, the separation is not that much. It is not really overlapping in this sense here, but it is very close to that interval. So, that is, it shows that the utility of Fisher's discriminant analysis. So, with that, let me stop here, and I will continue this topic in the next lectures. Thank you very much for listening to my talk.